Now let's go to twist mechanisms. There are two types of twist mechanisms. One is Ray-Dutt twist. Another one is Bailar twist. Ray-Dutt twist was first proposed by Ray and Dutt, and then later Bailar proposed another twist. Both of them are similar. But before going into that, I just would like to give a little bit of introduction about how octahedron is represented. Octahedron can be represented by these two ways. This way, one can show the bonds. These are these sticks represent the bonds, and I didn't put the balls for that representing the ligand donor atoms. But this is, the octahedron can be represented by this way also, and also by this way. And here, you will not see the bonds, and the metal is there in the center, and these are just only the imaginary lines. These imaginary lines are drawn by connecting the donor atoms just to get the shape of the octahedron. So this is octahedral geometry around the central metal ion, and the bonds are not visible. Of course, that means that actually we didn't put any sticks to show the bonds, and the metal is also not shown. This is one representation, and this is another representation. And this one has the central metal atom and also the bonds. I used this model for push-through and crossover mechanisms, and for Ray-Dutt and Bailar twists, I prefer to use this kind of model. And here we have two models of the same enantiomer. You can see that actually these and these are equivalent, and these and these are equivalent, and this and this are equivalent. Basically, both are the same enantiomer. And I keep this one for reference, and I'll perform Ray-Dutt as well as Bailar twists on this model. Before performing the twist, I would like to draw the relationship between the trigonal prism and the octahedron, because a trigonal prism is the transition state in both twists, that is Ray-Dutt and Bailar twists. When you hold the bottom triangular face and twist the upper triangular face by 60 degrees, now you got trigonal antiprism. That means here the two triangular faces are staggered. Earlier they were eclipsed in trigonal prism. This is called trigonal antiprism, but trigonal antiprism is nothing but the octahedron. And we can put the imaginary lines to complete the octahedron. I'm not changing the position of the atoms. I'm only putting the imaginary lines. So this is how one can draw the octahedron from the trigonal prism. Similarly, you can also get the trigonal prism structure from the octahedron. I just simply removed the three imaginary lines. Now you perform the 60 degrees twist in the reverse way, then you get the trigonal prism. So that's the relation between trigonal prism and the octahedron. So basically here we're going to convert this octahedron or the trigonal antiprism into trigonal prism. So one is associated with the C3 axis That's Bailar twist. Another one is not associated with the C3 axis, that is Ray-Dutt twist. So basically, you need to twist the one of the triangular faces by holding the other opposite triangular face by 60 degrees. Then you will get the trigonal prism. But here, since the bonds are really, these magnets are really strongly held, it's slightly difficult. So therefore, I just remove, without changing the position, I will just remove this so that it will be easier for twisting. And this one, and this one. So now it will be easy for me to twist it. Now you have the trigonal prism. And by twisting further 60 more degrees in the same direction, you will get back again your octahedron. But of course, you can also twist in the same way to get the same isomer, enantiomer. And if you want to get the other enantiomer, then you need to twist it further 60 degrees in the same direction. Now, once you twist it, then what you see is an octahedron again. And let's put these lines again. And you can see that it's a perfect octahedron. And compare with this enantiomer. And you can see that this is a perfect mirror image. These two mirror images, and these two are the mirror images, and these two are the mirror images. Similarly, one can do the Ray-Dutt twist and get back the same enantiomer. Now this is the mirror image. Now I perform the Ray-Dutt twist and get this enantiomer. Ray-Dutt twist does not involve a C3 axis. So this phase, the axis which is passing through this top phase and the bottom phase, this one is not a C3 axis. So now we need to perform the twist by holding the bottom phase and turning this phase. Now let us see. And again, for making the twist easier, I'm removing these imaginary lines without changing the position of the atoms. See, the position of the atoms is the same. Now 60 degrees. Now you got the trigonal prism transition state. Now it can come back to the original and give the same enantiomer, or from here it can turn further 60 more degrees. It can twist further 60 more degrees and give you the trigonal antiprism, that's nothing but the octahedron. And now this time you get the other enantiomer. So we started with the mirror image of this enantiomer, and now we got the same enantiomer. Let us check whether we have got the same enantiomer or not. You can see that this is the same enantiomer, not the mirror image. Equivalent positions, and these two are also the equivalent positions. Now let's take a look at the closer look at the intermediate in both Ray-Dutt and Bailar twist. It need not be intermediate, it can be the transition states. Let me perform a Bailar twist on this one and Ray-Dutt twist on this one. Both of them are the same enantiomers, but that doesn't matter. We're going to get the intermediate. I'll show you the difference between the intermediates. This one axis is not associated with the C3 axis. So, sorry, this is the C3 axis. So I'll do the Bailar twist on this one. So in order to get this, we need to get rid of some magnets so that our job becomes easier. Yeah, this magnet. So yeah, this is the intermediate in Bailar twist. Now let me perform Ray-Dutt twist on this. So this axis is not associated with the C3 axis. So therefore we will twist these two faces, this face and this face, along this axis. And let's see. And I need to get rid of some magnets in order to make our job easier. So I did not change the position of the atoms, it's still octahedron. So now twist it, and this is the transition state in Ray-Dutt mechanism. Take a look at both. The difference, note the difference here. This one has a D3H symmetry. So this is a C3 axis, and perpendicular to the C3 axis you have a horizontal plane. So that is a D3H symmetry, and this one, it has actually C2V symmetry. So that is the major difference between the Ray-Dutt and Bailar twist. In Ray-Dutt twist, the transition state has C2V symmetry, and in the Bailar twist, the transition state is having the D3H symmetry. The question is, which one operates when? There is no experimental proof to show that in some complexes Ray-Dutt twist operates, in some other complexes Bailar twist operates. But the computational studies show that if the bite, that is the distance between the donor atoms in the same chelate complex, the bite is shorter than this distance. This is the distance between the two adjacent donor atoms of two different chelates. When this bite is shorter than this distance, then the Bailar, and if it is the other way around, that means that actually the bite is larger than this distance, then the Ray-Dutt twist operates. There is a little bit of experimental evidence in favor of these computational studies, and in some complexes where they have the geometry of this trigonal prismatic geometry, it has been found that the bites are smaller. In other words, chelate complexes with smaller bites stabilize trigonal prismatic symmetry with trigonal prismatic geometry with the D3H symmetry. So that shows that actually the ligands with smaller bites undergo Bailar twists. And if bite and the distance, this bite and this distance are similar, then both mechanisms operate.